Hello everybody, welcome on the next third already lecture on the computational mathematics course. On today's lecture you will learn a new subject which is square-free decomposition of a polynomial and its application to symbolic integration of rational function. I know that last year in Aquila you had a course on numerical methods where you learn methods to numerically integrate any function. So to get a number which is definite integral of a function. On the contrary, today you will learn a symbolic method that can compute the indefinite integral. So instead of just a number which is a definite integral, we will get a symbolic function which is the symbolic exact integral antiderivative of a given rational function. So this is the subject of today's lecture. We start with the notion of square-freeness, especially square-freeness of polynomials. Uh, throughout throughout the lecture today, we'll work under the following assumption. So K will be a field that contains Q. So K contains the fields of rationals. Normally, K will be a field of real or complex numbers or possibly the field of rationals itself. It doesn't really matter. Important assumption is that the rationals are contained in K, and we will consider polynomials over K. The most basic definition of square-freeness is the following one. Assume that we have a ring and an element of a ring is said to be square-free if it is not divisible by a square of any non-unit of this ring. Possibly the simplest example are for integers. Because the definition is valid for any ring, so we'll start with integers. So example or for integers. So 6 is square-free. Since the only divisors are 1, 2, 3, and 6. So there is no square that could divide 6. In the ring of integer, no square can divide 6. On the other hand, 12 is not square-free. Because 2 square divides 12. There is a square that divides 12. This means that 12 is not square-free. Observe that for integers we can very easily decide whether an integer is square-free or not if we know the decomposition, the factorization of this integer. If we factorize the integer into prime numbers, then this integer is square-free if and only if all the primes in this factorization appear in the first power. So in case of 6 we have 2 times 3. Both integers appear at their first powers, so 6 is square-free. In case of 12, we have 2 squared times 3, so one of the primes appear at the second power, so 2 squared divides 12, and so 12 is not square-free. More general, if we factor an integer into product of power of primes, and at least one of these primes appear at a higher power, has higher exponent than 2, this means that this integer is not square-free. Exactly the same arguments applies to polynomials. So the ring of polynomials, like a ring of integers, is an Euclidean domain. So every polynomial can be factored, uniquely factored, into a product of a constant which is equal to the leading coefficient of f times the product of powers of monic irreducible polynomials that are pairwise distinct. And the same argument that I just used for integers implies that this polynomial is square-free if and only if all these exponents here are equal 1. So if and only if f factors into a product of first power of distinct irreducible monic polynomials. And so since a monic irreducible polynomial have only simple roots and these polynomials are pairwise distinct, this means that f is square-free if and only if all the roots of f are simple. Of course, we consider the roots in big enough field. So it can be the roots in the complex numbers or any field which is big enough to encompass all the roots. So f is square-free if and only if it has only simple roots. The square-free polynomials are very important from the point of view of computational mathematics, because if it has a simple root, real simple root, then it means this polynomial changes sign exactly at this root. The real simple root means the polynomial changes sign at this root, and it approaches this root in such a way that it is not tangent to OX. Visually, we have a real line, and we have some polynomial but I just plot a graph by hand. Then here we have a simple root. Because the polynomial changed sign and it was not tangent to the to the OX. Here we have a root of even multiplicity. It didn't change the sign here. This kind of root is very hard to detect. So the simple roots are very easy to detect, but the roots of even multiplicity are the hardest to detect. And finally, here, somewhere here, a root of odd multiplicity, because the polynomial changed sign, so the multiplicity was odd, but the multiplicity is greater than 1. It's not a simple. Why it's not simple? Because at this root the polynomial is tangent to OX. This kind of root is still, it's somewhere in the middle. It's not as hard to detect as root of even multiplicity because the polynomial changes sign, but the conversion rate of a root finder around such a root are usually worse than a simple root. So it is very important and very important to have only simple roots. And what I said, the polynomial with simple root are just the square-free polynomials. So this is the geometric intuition behind the square-free polynomials. Square-free polynomials are polynomials with only simple roots. Unlike integers, for polynomials, it is relatively easy to detect whether a polynomial is square-free or not. This is due to the fact that we can compute the derivative of a polynomial. The fact that we have a well-defined derivative of a polynomial make it very easy to compute, to check whether a polynomial is square-free or not. So the theorem says that if we have a polynomial over a field of characteristic 0 means that the rationals are contained in K, then the polynomial is square-free if and only if it is relatively prime to its derivative. So the greatest common divisor of polynomial and its derivative must equal 1. These two conditions are equivalent. And this right-hand side is computationally, it's very easy to compute. Because, okay, the polynomial we know from the first lecture how to compute the derivative, and we know how to compute the greatest common divisor, just use the Euclidean algorithm. So let's see the proof of this theorem. The proof of this theorem will depend on the so kind of a lemma or the condition. So we'll assume that xi is a root of f. So xi is a root of f of multiplicity k. K can be 1, so it can be a simple root, or k can be greater than 1, so it can be a not simple root. So if it's a root of f of multiplicity k, this means that f can be factored into x minus xi to the kth power times g, where this g does not vanish at xi any longer. So let us compute the derivative of f. We use the chain rule. We have a product. We have the derivative of a product. So this is a derivative of a first term times the second term, plus the first term times the derivative of a second term. So what we have? We have x minus xi to the k minus 1 power times k times g. So this is this part, plus it is x minus xi to the kth power times g prime. So this is this and this part. So x minus xi to the k minus 1 power appears in both terms, so we can take it out, and so we can write f prime in the following way. We have x minus xi to the k minus first power times this parenthesis, times this expression. And observe what happens if we evaluate f prime at xi. We have f prime of xi equals, it will be xi minus xi to the k minus 1 power times k times g of xi plus xi minus xi times g prime of xi. We have no idea what is k prime of xi, but xi minus xi is definitely 0. So this stuff is 0. K is a constant, and by assumption, we know that g of xi is non-zero. So this is non-zero. So this whole parenthesis, this whole form expression is non-zero. So all depends on this. This is either 0 if k is greater than 1, or it's 1 because we may have here, if k is equal 1, then this is a constant, this is just 1. If k is 1, then we have something to the 0th power, so this is polynomial to the 0th power, so it's 1. What we got is that xi, f prime vanishes at xi, but the derivative vanishes at xi if and only if the multiplicity is greater than 1. So xi is a common root of both f and its derivative if and only if it is a root of multiplicity greater than 1 of f. So how we can use it to prove the theorem? So we prove it in both ways. So first assume that f is square free, but suppose a contrario that this greatest common divisor is not 1. So we suppose a contrario that h, the greatest common divisor of f and f prime, is non-trivial. If it's non-trivial, it has some root somewhere in a field of complex numbers or whatever. There is some root of f. But okay, if it's a root of h, then h divides both. H divides f, h divides f prime. So since h of psi is 0, then it means that f prime of psi is 0 too. Okay, but if it's 0 too, from our lemma, it follows that the multiplicity of psi is strictly greater than 1. Okay, but if the multiplicity of any root is greater than 1, then f cannot be square free, but we assume that it is. So we had a contradiction. The contradiction follows from the fact that we supposed that this greatest common divisor is non-trivial. Okay, so this proves one implication. In order to prove the second implication, we again we assume that the greatest common divisor is 1, but we suppose a contrario that f is not square free. If it is not square free, then there must exist some root of f of multiplicity greater than 1. If it has a multiplicity greater than 1, then our condition asserts that f prime of psi is 0. So we have f prime of psi is 0. But then x minus psi divides f because psi is a root of f, and x minus psi divides f prime because psi is a root of f prime. Okay, but if x minus psi divides both f and f prime, it must divide the greatest common divisor. And if it divides the greatest common divisor, this greatest common divisor cannot be trivial because it is divisible by a non-trivial polynomial. This is again a contradiction. This contradiction follows from the fact that we supposed that f is not square free. This way we have proved this theorem. We can turn this theorem directly into an algorithm that verifies whether a polynomial is square free or not. So given a polynomial f over a field of characteristic 0, what we do, it's exactly what we saw in the theorem. We compute the derivative using the algorithm for the first lecture. Then we apply the Euclidean algorithm and we compute the greatest common divisor of f and f prime, and then we check whether this greatest common divisor is invertible, it's 1 or is not. And this says whether this polynomial is square free or not. The assumption that the field has characteristic 0, so in other words, that the field contains the rationals, is indispensable. In fact, this theorem no longer holds if we forget about this assumption. We can see it on this simple counterexample. So for k, we take a field of rational functions over the finite field with p elements, over the Galois field of p elements. And our polynomial f is x to the pth power xp minus t. Here the variable is x. The t is element of a field of constants. Of course, it's a variable over fp, but the whole field of constants is fp of t. So if we compute the derivative of f, what we have is f prime, it is p times x to the p minus 1 power minus, and t is a constant. So the derivative of a constant is 0. So what we have now, p, in our field p is 0, we have a field of p elements. So this is 0. So what we see is that f prime is 0.
And the greatest common divisor of anything and 0 is, of course, this anything. So the greatest common divisor of f and f prime is just f. And it is not 1. But on the other hand, the polynomial f is irreducible. This polynomial is irreducible, so it is trivially square free, because in the decomposition, in a factorization into irreducible factors, there is only one factor, f itself, and if it's of exponent 1. So f is square free, but this condition does no longer hold. This is because our field does not contain the rationals. One may wonder why I take such a complicated field of constants. Why I didn't take just FP? Well, the reason is that over a finite field, this theorem still holds. So in our theorem, we can change assumptions and say that either K contains Q or the field K is finite. In both cases, this theorem holds. But in general, if we have infinite field which does not contain the rationals, then this theorem is no longer true. So that's where this assumption comes from. Now when we know what the square-free polynomial is, we can go on and define square-free decomposition. Recall that over any field, a polynomial, as before, a polynomial can be factored into a product of powers of irreducible monic polynomials times a constant. The constant is just the leading coefficient of f. So now we will group elements in this product. We will group elements according to their exponents. So first, group together, just gather all these polynomials here that has exponents 1. And we will call this G1. Then we group together, we gather these polynomials here that has exponents 2, and the product of them, we call the product of them G2, and so on and so on. We define Gi to be the product of these polynomials, these irreducible factors of f that have exponents I. So Gi is the product of all these pj's with exponents I. Observe that we do not have any exponent here. We do not have an exponent here. So Gi is a product of first powers of any of these irreducible polynomials. So in particular, Gi is square free itself. So if we just rearrange the terms in this product, gathering the irreducible polynomials of the same exponents, then we can write, we got the following observation. We can write C uniquely in a following product. It's this constant. We do not really care about this constant. The constant is not important at all. Times the product of powers of monic and square-free polynomials. G1 to the first power, G2 to the second power, and so on and so on. And these square-free polynomials are pairwise coprime, and this thing is called the square-free decomposition of f. Of course, we define this square-free decomposition using the full factorization of f. But the important point is that in order to compute this square-free decomposition, we do not need the full factorization of f. This is a big difference between the integers and the polynomials. I'm not aware of any algorithm that could find the square-free decomposition of an integer in simpler way. We would have a lower complexity than the full factorization of an integer. On the other hand, the square-free decomposition of a polynomial is very easy, and it's much easier than the full factorization of polynomials. In fact, for most algorithms of factorization of polynomials, the square-free decomposition is the first step. So that's why we consider it here. And of course, this fact that the square-free polynomials have simple roots, which is important for finding the roots. So our first observation is, okay, we gathered the polynomials, this irreducible factor with the same exponents. So in particular, the roots of any gi are exactly the roots of f of multiplicity gi, because they are pairwise coprime, so they do not have common roots. So if f has a root of multiplicity 1, it must be a root of g1. If f has a root of multiplicity 2, then it must be a root of g2, because it's only place where the roots appear with exponents 2. We have exponent 2 here. And so on and so on. If f has a root of multiplicity gi, then it must be a root of multiplicity I, then it must be a root of gi. So let's see what it really is. If somehow we know the decomposition, if we know the factorization, usually we do not know. And we will see the examples how it works when we do not know the factorization. But if we know the factorization, so okay, we gather this element because it has exponent 1, and this element, it has exponent 1. So this is our g1, this is g1. Now we gather this guy and this guy, they have exponent 2. So this is our g2 without these exponents. So this is g2 squared. And now we take this guy and this guy. So this here, this polynomial in the parenthesis is our g3, and it appears with exponent 3. What we got is that f is a product of powers, of successive powers of square-free polynomials. These gi's are called square-free factors of f. There's a number of different algorithms for finding square-free decomposition. The oldest one, the first one, is due to Tobey and Horowitz, and is over 50 years old. It was independently discovered by Tobey in 1967 in his PhD thesis, and by Horowitz in 1969 in his PhD thesis. They work independently, they didn't cooperate. This algorithm was independently discovered by both of them. And since then, there appeared a number of other algorithms, Musser, Jan, Gerhardt, and Gurtzen, Zweig, Shetman. As you can see, the newest algorithm, the most modern one, is only 3 years old. It appeared. It was published in 2017, 3 years ago. On this lecture, we will discuss the oldest. It is also the simplest of all these algorithms, the algorithm that is due to Tobey and Horowitz. If you are interested in other algorithms, then I strongly encourage you to look into the lecture notes. In lecture notes, you will find the other algorithms, except Gerhardt's algorithm, which will appear in the lecture notes in one day, but is not yet there. I'm planning to write about it, but I had no time so far. But all our algorithms are in the lecture notes, so I encourage you to look into it. However, we will concentrate on this first oldest of all these algorithms. In Tobey-Horowitz algorithm, we need to define 3 finite sequences of polynomials: ai, bi, and gi. Gi are exactly the elements we are looking for. Gi are the square-free factors of f that we are looking for. ai and bi are auxiliary sequences that will help us compute the gi. First, we define the sequence ai. We define it in the following way. We take a0 to be the polynomial f, and ai to be the greatest common divisor of its predecessor and its derivative. I will derive the formula for A1, and this formula can be successively inductively generalized for all other AI. So our polynomial A0 is just f, and it's a product C times G1 times G2 square times G3 cube, and so on and so on and so on, gk to the kth power, where we are looking for these gi's. So these gi's are the sought polynomials, they are unknown polynomials. So now what is the derivative of a0? A0 prime, this is a derivative of the product, so it's a sum where in each term we have a derivative of one of these terms of this product. So C is a constant, so we can just rewrite it. Then we have G1 prime times G2 square times G3 cube time and so on, gk to the kth power, plus now we will have a derivative of G2. So we'll have 2 times C times G2 prime times G1 times G2. Okay, now the derivative of G2 square is 2 times G2 prime times G2. So I write it this way, and times G3 cube, and so on, gk to the kth power. Let me compute one more step, and now we'll have the derivative of G3. So this will be 3 times G3 squared times G3 prime. So we have 3 times C times G3 prime, the derivative, times G1 times G2 square times G3 square again, times and so on, gk k, and so on. This sum runs over all the indices from 1 to k. The last term is k times C times gk prime times G1 times G2 square times G3 cube, and so on, gk minus 1 to the power k minus 1 times gkk. And now A1 is the greatest common divisor of A0 and A1. Okay, the constant C appears everywhere, and so we don't care about it, we just rewrite it. Now we look at G1. G1 is here, G1 is here, G1 is here, G1 is everywhere except the first term. In this first term, we do not have G1. We have G1 prime, which is relatively prime to G1 because G1 is square free. It's square free, so it's relatively prime to its derivative. So G1 and G1 prime are relatively prime. G1 and Gi for any I greater than 1 are relatively prime because they were relatively prime from the very beginning. So this whole expression, this whole product is not divisible by G1. All these products here are divisible by G1, but this product is not divisible by G1. So the whole sum is not divisible by G1. So we do not have G1 here. Okay, let's look at G2. We have G2 square here, 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 but here we have only G2 to the first power. And again, all these products here and here, all these products are divisible by G2 square, but this product is divisible only by G2, not G2 square, just G2. So the whole sum So the whole a0 prime is divisible by g2 to the first power. F is divisible by g2 to the second power. a0 is divisible by g2 to the second power. But a0 prime, the derivative, is divisible by g2 to the first power only. So in this greatest common divisor, we have g2 to the first power. Now we look at g3. G3 here appears with, in the fourth power, we have G3 cube. Here we have G3 cube. Here we have G3 cube. Here we have G3 cube. But here we have G3 to the second power only. So again, the whole sum, this A0 prime, this whole sum is divisible by G3 to the second power only, while A0 was divisible by G3 to the fourth power. So all in all, in this greatest common divisor, we have G3 square. And so on and so on. Finally, if we look at GK, we will see, okay, this should be K minus 1 here, my mistake. We see that the GK appears in the K minus first power. So this is A1. And so if we look here, this A1 starts, it just reduces the exponent by 1. When we go from A0 to A1, we reduce the exponent by 1. So in particular, that first term, G1 drops, it just disappears. It is to the exponent 0, so it's 1, it disappears. And all the other appear with exponent reduced by 1. We can now inductively apply the same thing to all the remaining AIs. And what we get is that AI is just C times the product from gi plus 1, starting from gi plus 1 to the first power, gi plus 2 to the second power, and so on, till the gk to the k minus 1 power. So this is AI. This is the first of these three sequences. Now we take the second sequence, BI. BI is defined to be AI minus 1 over AI. And again, we can compute how much it is. We have that this is C times, okay, using the formula which is derived above, this is C times GI plus 1 square times GI plus 2 cube, and so on, gk to the power k minus I plus 1 over C times gi plus 1, gi plus 2 square times gk to the power k minus I. And if we just now cancel whatever we can, we cancel C, we cancel this exponent with this guy, we cancel this exponent with this guy, and we cancel this exponent with this guy. So what we got all in all is that BI is a product starting from GI up to GK. GI, it's a product of the first powers of all the square free factors of F starting from GI. Now, when we have this BI, we can easily compute the GI. It's all in all we need is to divide the two successive elements. So BI starts from GI, BI plus 1 starts from GI plus 1, so all the terms starting from GI plus 1 up to GK cancel, and what is left is this GI. We can easily write it now as an algorithm. As I said, this algorithm was independently invented by Tobey in his PhD thesis in 1967 and Horowitz in his PhD thesis in 1961. We take a polynomial f, it can be a monic or not, doesn't matter, and we produce the square free factors of g1 to gk of f. we define all these three sequences. We start with A0 equal F. A1 is the greatest common divisor of A0 and A0 prime, and the B1 is a quotient of A0 over A1, is the quotient of these two first terms. Now, when we stop when bi is 1, because bi is 1 means we do not have any more factors here. We are run out of gi's. So as long as bi is not 1, is not a unit, we do this thing. We compute the successive element of the first sequence, we compute the successive element of the second sequence, and we compute the fraction bi over bi plus 1. And according to our formula, this is the next square free factor of f. So when we get down to bi equal 1, it means we computed all the gi's and we can return them. It's most easy to present it in form of a diagram. So we start with a0, which is just our polynomial f. Next, we compute a1, just taking the greatest common divisor of a0 and its derivative. Now, when we have these two elements, we can compute b1, just dividing them. Now we compute a2. Now we have a1 and a2. We compute b2. Now when we have b1 and b2, we can find a first square free factors of both of them, of b1 and b2, and this is g1. And we repeat the process. We compute a3, b3, and g2, and so on, till we find gk. Let me show you an explicit example how we can compute this thing. So we have this polynomial. We have this polynomial of degree 7. We start with a0 equals f, so this is this polynomial. We compute a1 is the greatest common divisor of a0 and a0 prime, and using Euclidean algorithm we see that is this polynomial. Now we have a0 and a1, so we can compute b1. So this is b1. And we repeat the step. We compute a2, which is this guy, and we compute the fraction of these two guys, the quotient of these two guys, so this is b2. Now we have b1 and b2, so it's very easy to compute gi. It can be done even by heart. This is x squared minus 1, x4 minus 1, so it's x squared plus 1, so g1 is 1 plus x squared. Okay, we factor f to this. This is the first square free factor, and we compute a3, it's 1. We compute the fraction of these two guys, the quotient. This is b3, and we compute the quotient of b2 and b3. This is x minus 1. So this is the second factor here. g1, g2 square. And finally, we have a4 equal 1. b4 is 1 over 1, it's 1. So where that's the 1, and we compute the quotient of these two guys, so it's x plus 1. So now we stop, and the last term is 1 plus x cubed. So this is the square free factorization of our polynomial. g1, g2 square, g3 cube. That's how Tobey-Horowitz algorithm works. There is a notion very closely related to the square free decomposition. It's called the radical of a polynomial, or more generally, radical of any element in a unique factorization domain. So if we have a polynomial and we can factor it into product of powers of square of irreducible polynomials, then the product of these irreducible factors of f, but with first exponents and without this unit, is called the radical of f. The same idea applies to the integers, and maybe for integers it's easier to understand what the radical is. So let me compute the radical of an integer. So example in the integers. So let me compute the radical of minus 12. Minus 12 is the radical of, and I can factor minus 12 to the unit, minus 1, times 2 square times 3. And the radical is, okay, we drop the unit, so we drop this minus 1, and we drop all the exponents. So we write 2 to the first power times 3 to the first power, so it's 6. So the radical of minus 12 is 6. The same is the radical of 12. The same is the radical of 24, because 24 is 2 square, 2 cube times 3. So we drop the exponents and we have 2 times 3 is 6. So this is the idea of the radical. It applies both to polynomials and the integers. So from the way we derive the Tobey-Horowitz algorithm, we can immediately see that, okay, the product, all these GIs are the products of the PIs to the first powers. So the product of all the GIs here is the same as this product. So this is the radical. Radical of f is G1 to GK. But G1 to GK was the first of these elements in the auxiliary sequence BI. So radical of f is nothing else but the BI, the first element of this sequence. So it was computed as A0 over A1, A0 over the greatest common divisor A0, A0 prime. So the radical of f can be computed as f over the greatest common divisor of f and f prime. In other words, the radical of f is a polynomial that has exactly the same roots as f, but all the roots of the radical are simple. Again, we can imagine it in a geometric way. So like before, I will plot something that must be a graph of this polynomial. So we have a simple root, we have, let's say, a double root here, and supposedly a triple root here. This is our f. This is our f. And then the radical of f will be a polynomial, very similar to it. It will pass exactly the same, it will have exactly the same roots. I suppose that here maybe the picture is not very perfect, but I wanted to draw it in this way, that it was a root here, but it changes sign. It has simple roots everywhere. So our original polynomial, maybe I will improve this picture. Okay, this was expected to have a root here. So this is the radical. What I draw here would be the radical of f. So it has the same roots. It vanishes exactly at the same points ff. But now all the roots are simple. This is the radical. And now let me do the first application of the square-free decomposition. The first and most simple application of the square-free decomposition is to detect when a polynomial is a power of another polynomial. So f is a polynomial, and we want to know if it is an nth power of another polynomial. If we have the square-free decomposition of f, this is really easy to answer this. Okay, this constant term must be the nth power in the field of constants. That's one condition. And the cover condition, because these polynomials are square-free, they are not powers of anything. So the only way in which f can be the nth power of something is that in this product we have only the nth powers. Only the nth powers. So the only terms that appear here, the only terms which are not trivial, must be Gn, G2n, G3n, and so on. The only non-trivial Gi's must be those where n divides the index I. If it is true, if it is the case, then this polynomial G is of this form. This is the nth root of C times, okay, Gn to the nth power was a factor of f, so we compute the nth root of it, so it's Gn. We divide the exponent by n. Now in f we have G2n to 2n. Now we divide 2n by n, so we have G2n to 2 and the square of G2n, and now we and so on and so on. The only terms here are those with indices divisible by n, and the last one will be something like Gmn to the nth power. So this is the simplest application of square-free decomposition. A more important application of square-free decomposition is the partial fraction decomposition. Let me explain what it is. Although we will be most interested in partial fraction decomposition of a rational function, I will start with partial fraction decomposition of a rational number because, again, this is somehow easier to understand. This is closer to what we are used to for years starting from primary school. So suppose that we have a rational number 5 over 12. Then a number 12 can be factored as a product 3 times 4. So we can write it as 5 times 1 over 3 times 4, where the two factors in the denominator are relatively prime. So we have that 1 is the greatest common divisor of 3 and 4, and using the Bezout identity, we can write 1 as a linear combination of 3 and 4. We can write it as a minus 1 times 3 plus 1 times 4. So we will now replace, we will use this fact, this equality, to replace this one here. So we can write it as 5 times minus 1 times 3 plus 5 times 1 times 4 over 3 times 4. Now we can decompose into this fraction as a sum of two fractions. So this is minus 5 times 3 over 3 times 4 plus 5 times 4 over 3 times 4. And now we can cancel the 3 here and 4 here, so that we got minus 5 over 4 plus 5 over 3. This is a partial fraction decomposition of the fraction 5 over 12. However, these two fractions are not simple. The numerator have greater absolute values than the denominator. So we can write it as minus 1 plus 3 over 4 plus 1 plus 2 over 3. And observe that these two integral parts cancel. They must cancel. This is clear that they must cancel because here we do not have an integral part. So we cannot have an integral part of the right-hand side. If the left-hand side is equal to the right-hand side, and we do not have any integral part on the left-hand side, we cannot have a an integral part on the right hand side. So all in all, what we got is 3 over 4 plus 2 over 3. We can now use the same thing, but with respect to the rational function, or in fact to any fraction over a unique factorization domain. So when we have, once we have a fraction, and we can decompose and we can factor the denominator into a product of two relatively prime factors, then by the Bezier identity, there are some elements alpha and beta such that one is a linear combination alpha A plus beta B. And now, as I presented in the previously, we just replace this fraction as f times 1 over A times B. We replace 1 by this linear combination, and we split this fraction into a sum of two fractions, cancelling the common terms, so cancelling B here and A here. So this is a partial fraction decomposition, PFD in short. We can use this with a rational function as follows. We start with a rational function. First of all, we just make this fraction simple. We just divide. In case it is possible that the numerator will have a degree greater than the denominator, in such a case, we just divide with a remainder. We compute the quotient and the remainder of f over g, and this quotient with g is cancelled, and this quotient is the polynomial part, the counterpart of the rational part of the integral part. So this is a polynomial part of this fraction. And now for this fraction, we decompose the denominator into square-free parts. We find the square-free decomposition, square-free factorization of g, and for every of these square-free parts, we apply the procedure that I described on the previous slide. So this way, we decompose this original fraction, this original rational function, into a sum of polynomial and sum of fractions where each denominator is a power of a square-free polynomial, of a square-free factor of the original denominator. So all in all, we have proved the following observation. If f over k is a rational function and we have decomposition of and we have square-free decomposition of the denominator, this function decomposes into a sum of this form. This is called the incomplete square-free partial fraction decomposition. The name is quite long, so we will shortly write ESPFD for this. The formal algorithm that computes this ESPFD works like this. We start with f over g. First of all, we compute this polynomial part as a quotient of f over g, and we leave the remainder as the numerator. Then we compute the square-free decomposition of the denominator, and we cancel the numerator and denominator. We just get rid of this constant term in the denominator, and we move it to the numerator. After that, we just loop over these square-free factors. We loop over these square-free factors, and for every such a square-free factor, we just split the denominator into the given square-free factor and all the rest. Using, of course, this gi and this bi are relatively prime, so we can use the extended Euclidean algorithm to compute the Bezier coefficient alpha and beta, such that alpha bi plus beta gi to the ith power give us 1. And now we apply the formula that I just derived. We replace the numerator by such an expression in one fraction, and the numerator of the other fraction is this expression. Observe that both times we compute the reminders. The quotient must cancel from because there's no more integral parts or polynomial parts in our numerator, so these two quotients from here and here will cancel, and we are left only with the reminders. And the last reminder is what is left is this ak minus 1, the last numerator where we are left. So all in all, we arrive at this sequence of fractions, which sum up to f over g. Let me show you an explicit example how it works. We start with such a big, quite ugly rational function, and we want to decompose it. We want to write it as in form of a sum of simple fractions. First of all, we divide the numerator by the denominator. We compute the remainder, quotient and remainder. We have degree 8 in the numerator and degree 6 in the denominator, so we have a non-trivial quotient. So if we compute, then the quotient is x squared minus x plus 2, so this is the polynomial part, and we are left only with this fraction, where it's a proper fraction because the numerator has a lower degree than the denominator. Now, in the next step, we compute the square-free decomposition of the denominator, and we see that the denominator is a product of g1, g2 square, and g3 cube. And we separately treat the g1 and the rest. So this g2 squared times g3 cube is our b1, and g1 is here. And this is our denominator. And these two guys are relatively prime. So we can, using extended Euclidean algorithm, we can find the Bezout coefficient alpha and beta. Alpha is 1 over 8 and beta is this polynomial. So now we replace the numerator by a0 times 1, and we replace this 1 by this formula, and we split this fraction into a sum of two fractions, a0 times alpha and a0 times beta. These are again improper fractions. The numerators has greater degrees than the denominators, so we compute the quotient and the reminders. Of course, this quotient will cancel. So the remainder of this numerator modulo 1 plus x is 3. So we replace it by 3 over 1 plus x. And the quotient and the remainder of this numerator modulo the denominator is a1 equal, well, this polynomial of degree 4. So we replace it by this formula. So our original rational function simplifies to this formula, but we still have a product of two relatively prime polynomials in the denominator, so we can repeat this procedure and split this fraction into a sum of two fractions. So this is our g2 squared and this is our b2. They are relatively prime. So again, using the extended Euclidean algorithm, we find the Bezout coefficient alpha and beta. Alpha is this guy and beta is this guy. So we split this fraction into a sum of two fractions, a1 times alpha and a1 times beta. And again, these fraction are improper. So we compute the reminders. The remainder of this guy times of this guy over this guy is 5 plus x. So we have 5 plus x over 2 plus x squared. and the remainder of this guy over this guy is 7 minus 2x. So all in all, we got this this expression. So we finally have computed the incomplete square-free partial fraction decomposition of our original rational function. Our original rational function was quite complicated, and we simplified it. We substantially simplified into a sum of such much simpler rational functions. The name incomplete square-free partial fraction decomposition suggests that there should be something which is complete, and in fact it is. We can further split any of these guys here into a sum of even simple fractions. This will apply an additional step for all these fractions where the denominators are non-trivial powers of square-free polynomials. So this guy, the polynomial part is okay. This guy where we have only the square-free denominator is okay. But for these two guys, when we have a power of square-free denominators, we can apply an additional step. How this additional step look like is the following one. So suppose that we have some fi over gi to the ith power. What we can do, we can divide fi modulo gi, not gi to the ith power, but the modulo gi without this exponent. So we can write fi as some quotient times gi plus some remainder over gi to the ith power. And now we can decompose this fraction into a sum of two fractions, cancelling the gi. So what we have is r over gi to the ith power plus q times gi, but this is gi cancel, over gi to the power I minus 1. And now for this guy, we repeat the process. So we factor out, we split out, we have split out this this fraction where the numerator has a degree lower than the degree of gi, not gi to the ith power, but gi itself. The numerator has a degree lower than gi itself, and some other fraction where the exponents is lower. And now we will repeat, and we will have some new r over gi to the I minus 1 power, and some new q over gi to I minus 2, and so on and so on. Finally, we will see this guy, this kind of sum here. So all in all, the algorithm that I just highlighted formally works like this. We are given a rational function, and we will produce the complete decomposition of this rational function. First of all, we compute the incomplete decomposition. The first two terms, the first two summands are okay. They are okay. And starting from this summand, from G2, from the index 2, we do a loop. We loop here over all the summands starting from index 2 up to the end. And for each summand, we do what I just presented. So we compute the quotient and the remainder. We split out remainder over the gi to the jth power, and we update the numerator to be the quotient. This is a numerator, this is the part where we split out, and we decrease the j. So we repeat this guy. So for every such a summand, we have another loop where j starts from the exponent and goes down, starts from the exponent and goes down to 1, and we one by one we split off consecutive fractions. This will eventually produce this expression. Again, let me show you an example. We have this same rational function. We have already computed the incomplete square-free partial fraction decomposition, and what is left are these two guys. So let me show you, for example, how we can split this guy here. So we have x plus 5 over x plus 2 square. X plus 5 is nothing else but 1 times x plus 2 plus 3. So the quotient is 1, the remainder is 3, x plus 2 square, and we split it into a sum of two fractions. So this is 1 over x plus 2 plus 3 over x plus 2 square, and here the numerator have degrees lower than this square-free polynomial. And this actually works like this. I have already presented how we split this guy, and we repeat the same thing for this guy, and we split it off into a sum of 3 fractions. The first fraction contains 0, so it is just 0, it cancels, and all in all we have the following complete square-free partial fraction decomposition. One of the main applications of square-free partial fraction decomposition or partial fraction decomposition in general is for symbolic integration of rational functions. In Akira last year, you had the course on numerical methods, and there you learn the numerical methods for integration of different functions. You learn the numerical approach to computing the integrals. Now I will present the symbolic approach to computing integrals. So while the numerical method is very good and it gives you the definite integral, when you want to find the indefinite integral, so you want to find not just a number, but you want to find a function which is the antiderivative of a given rational function, then you must use the symbolic methods. And these are the methods that I will somehow, to some extent, I will explain today on the rest of this lecture. We are given a rational function and we want to find the antiderivative of this function. The special case, very simple case, is when the rational function is just a polynomial. If we have just a polynomial, then computation of the antiderivative is very trivial, because everyone knows that if a is a constant and we have such a polynomial, then the antiderivative is a over n plus 1 to x to the power n plus 1 plus some new symbolic constant. So when we apply this together with the linearity of integral to this polynomial, what we have? The constant term of our antiderivative is a new symbolic constant, some new constant c, and for every of these summands, of every of these terms of a polynomial, we just compute the corresponding term of the polynomial, which is the antiderivative. So it's 1 over I plus 1 is like this, times this coefficient which is here. Of course, this will be the I plus 1 coefficient of a new polynomial. So all in all, this polynomial look like this. And this is actually the proof of the correctness of this algorithm. So our problem is to compute this indefinite integral, this antiderivative. What we can do is, first of all, we can apply the complete square-free partial fraction decomposition. We can write this rational function as a sum of simpler rational function, where the denominators are the powers of square-free polynomials. Now we can apply a linearity to it, and we can write this sum, this integral of a sum as a sum of integrals. Now when we look at the first term, this is an antiderivative of a polynomial, and our last algorithm answered this question, so this is solved. So what is left is this guy. We need to find the antiderivative of a rational function where the denominator is a power of a square-free polynomial. And to this end, we will use so-called Hermite reduction. So let me explain it as follows. We need to compute this integral b to n, where b is square free. Since it is square free, it means, from what we saw on the beginning of this lecture, that it is relatively prime to its derivative. So the greatest common divisor of b and b prime is just 1. But now the Bezout identity implies that there are some polynomials c and d such that c times b plus d times b prime is 1 for some polynomial c and d. So we will use, again as before, we will use this identity inside our integral, just multiplying the numerator by 1. This is the same trick that you have already observed earlier today. So our integral a over b to the power n can be written in this form. It's a times 1 over bn. So this is integral a times c b over bn plus a times d b prime over bn. Now this b here and this exponent cancels. So we have, and we use the linearity of the integral. So this is a c over b to the power n minus 1 plus exponent of a d b prime over b to the power n. And we will now concentrate on this integral, and we will use integration in parts. Integration in parts. So we know that the integral of u times v prime is nothing else but u times v minus the integral u primes times v. So in our case, we have a d times b prime over bn. So this will be our u, and this is our v prime. Observe what this antiderivative of v prime. So our v is 1 over, okay, b to the power n minus 1 times 1 minus n. Indeed, if we compute v prime, then we will have the derivative 1 over 1 minus n is a constant, times. Now we have a derivative of we use a chain rule. So we have a derivative of b prime times the derivative of something to the n minus 1 power. So this will be minus n minus 1. So 1 minus n, and b to the power 1 less, so n minus, it was minus n minus 1 minus 1, so minus n plus 1 minus 1, so it's minus n, so it's n here. These two guys cancel, and we have indeed this form. So using the integration in parts, we see that this guy is a times d times v sum 1 over 1 minus n times b to the power n minus 1 minus this integral u prime v. So this is a d prime over 1 minus n b to the n minus 1. So this is the same guy as above. So we can write this whole integral in the following way. So what we got is that a over b to the power n is integral a times c over b to the power n minus 1 plus, okay, let me write it this way. It will be 1 over n minus 1 times a d over b to the power n minus 1 minus integral 1 over 1 minus n times a d prime over b to the power n minus 1. And now we can again use the linearity of the integral and write it as, okay, it will be a d over n minus 1 over b n minus 1 plus a c minus 1 over 1 minus n a d prime over b n minus 1. Observe now that we have reduced the exponent in the denominator. We have dropped the exponent by 1. So this is the Hermite reduction. In one step of this Hermite reduction, we drop the exponent of the denominator by 1. Repeating this procedure, if we now repeat this procedure for this integral, we will split off a fraction with bn minus 2 in denominator, and we got the exponent with b to the power n minus 1 in the denominator. And again we will repeat this procedure till n drops to 1, and then we will have an integral where the denominator will be a square-free polynomial of just a square-free polynomial without any exponent. So all in all, the procedure that I just highlighted works like this. We are given a rational function where the denominator is a power of square-free polynomial. As a result, we got two fractions such that this left-hand side, this integral, is a sum of this fraction plus this integral where the denominator is just a square-free polynomial without an exponent. And the procedure is just the application of what I just wrote. So we start with, okay, 0 and a over bn. So a is 0, b is a. And our exponent is, okay, and I will start with exponent a with the index n minus 1, so we'll just the next exponents we will produce. And as I did on the previous, just 2 minutes ago, we use the extended Euclidean algorithm to find the Bezout coefficient C and D such that the linear combination of C times B plus D times B prime is 1. And as long as this exponent is not 1, as long as we have an exponent greater than 1, we just compute the two parts. We just add to this guy this expression. Observe that this is exactly this expression here. And we update the numerator here to this expression, and again observe that this is just this expression. These two guys are equal, where B is just the current numerator. And we repeat it till we drop the exponent to 1. After that, we just split the polynomial part, so we compute the quotient and the remainder of B over the denominator. So our quotient Q is added to the antiderivative. We compute the antiderivative. It is added to our A, and we are left with the numerator R, which is this guy. So these two guys are the result of our algorithm. So after we apply this Hermite reduction, we are left with the integral of this form, A over B, where B is just a square-free and monic polynomial. And how to compute this antiderivative, this integral? Actually, this is a standard thing. Such an integral where the denominator splits into is a product of linear terms, x minus psi I, where psi I are distinct roots of a denominator, is such a sum. The proof of this fact is trivial. Proof: just compute the derivatives of both sides. There's nothing more. If you just compute the, here we have h over g, and you compute the derivative of this guy, you got h over g, and you see that this is actually true. So the whole algorithm, the whole complete algorithm for the integration of rational function look like this. We are given such an integral, a rational function. We want to integrate it. First of all, we compute the complete square-free partial fraction decomposition. We split it into a sum of such simple fractions. This is a polynomial, so we compute the antiderivative using this simple algorithm that I explained a few minutes ago. And now for all these guys, we just loop over all these fractions, and we, for every fraction where the exponent is greater than 1, we apply Hermite reduction to get, well, some rational function and an integral where the denominator is now a square-free polynomial. For this square-free polynomial, we need to find the roots, and we will spend a couple of lectures, and the next lecture and a couple of our lecture will spend on ways to compute the roots of a polynomial. This will be this step here will be a subject of incoming lectures. So we will learn how to find the roots of polynomials. So applying the methods that we will develop, we will find the roots of these polynomials. So we apply this observation that was just 2 slides ago to compute the antiderivative of this guy. So this is the antiderivative of this integral, and summing all over this integral and this the antiderivative of a polynomial part, we arrive at the complete answer. We arrive at the antiderivative of our rational function, of the indefinite integral of a rational function, symbolic integral. So this is not just a number. This is not a definite integral from some a to some b. This is just a function. This is explicit function that is an antiderivative of this rational function. Let me show you an example. So we are back at our ugly, big, complicated rational function. We have already computed the complete square-free partial fraction decomposition, so it looks like this. So our integral can be replaced by this integral of a long sum. Now we use the linearity of the integral and we split it into a sum of integrals. Now the first part here is the antiderivative of a polynomial, so we can compute it using the procedure what was before. Now we are left these guys. Here the denominators are of degree have exponent 1, but in the second line the denominators have exponent 2, 2, and 3. So for all these three guys we apply Hermite reduction. So we reduce the first one and we have this rational function and this integral here is 0, so it cancels. Now we apply the same guy here. We have 2 over 3 plus x and this integral which is 0, so it cancels. And we apply the Hermite reduction to this guy and we got this rational function and this integral with 0 here, so it cancels. So all in all, we are left with such an expression. Here we have a symbolic constant. Here we have an explicitly given rational function. And here we have two integrals left to compute. For these two integrals, we apply the observation that was here just a few minutes ago. Here we explicit, these functions are so simple that we just see the roots. Here the root is -1, here a root is -2. So when we apply this formula, we see that the whole integral, the symbolic integration, symbolic indefinite integral has this formula. So we computed this integral of this big function. So this is a way to compute the integral of any rational function modulo the ability to find the roots of square-free polynomials that will be explained on the next lectures. At the very end of this lecture, let me mention that rational functions are not the only one. This is not the only class for which we can compute integrals symbolically. Of course, not for every function there are appropriate algorithms. There are functions which we cannot integrate symbolically, but the class of functions for which there are algorithms are much broader than just rational function. So for everyone interested in this subject, I strongly encourage you to take a look at the books and the literature for this course. So in particular, the Gatton and Gerhardt modern computer algebra or Winkler polynomial algorithms in computer algebra are good sources to look at. Moreover, a symbolic summation is very similar to integration from a mathematical point of view. And in fact, for symbolic summation, we also have appropriate algorithms.
This is all for today. Thank you very much for your attention. As always, I strongly encourage you to have a look at the course notes. The link to the course notes is, as always, below the movie. So we meet again in 2 weeks on the next lecture, and the few following lectures will concentrate on the problem of finding, actually computing or approximating the roots, real roots of a given polynomial. already today in this algorithm of indefinite integral, you have observed that the problem of finding roots of square-free polynomial is one of necessary components that we need to learn, and this will be subject of the following two lectures. See you. So this is all for today, and see you in 2 weeks on the next lecture.